I kindly ask Chen Lai, hi, nice to meet you, to show up. And Chen is going to speak about unify and fast deploying GenAI on Edge with ExecuTorch. The floor is yours, Chen.
Great, thank you. Hi everyone, my name is Chen and I'm from PyTorch Edge team at Meta. So my talk today is about fast and unified deploying GenAI on Edge with ExecuTorch. As we know, PyTorch has become the unified framework for working with ML models. Most researchers start from PyTorch, train with PyTorch, and deploy with PyTorch on server side. However, deploying models on Edge is just more difficult because of challenges like constrained memory, compute, and heterogeneity of hardware devices. This often leads to fragmented ad hoc solutions. So, can we apply a unified edge frameworks to generated AI systems while remaining performant? ExecuTorch is our answer, and I will introduce it in a bit shortly. So let's take a step back and see why people are interested in running ML models on Edge. Well, there has been an emergence of running AI models on devices, including mobile, biosensors, IoT, etc., because of listed opportunities like low latency, privacy, etc. However, there are definitely challenges. So edge devices usually has like lower battery life, less memory, and most of them also has thermal requirements. The diversity of the hardwares are also just much more broader than server space. Here, I would like to introduce ExecuTorch. It's a fast and unified solution. ExecuTorch is the solution from PyTorch. To run PyTorch models on edge devices, we aim to support iOS, Android, and embedded device. It's fully open source, and we are working with Apple, ARM, Qualcomm, and MediaTek to support their hardwares to achieve the most optimum performance. ExecuTorch starts from PyTorch model, run through torch.export to get a graph. After compilation and transformation, it will generate the ExecuTorch program. On edge devices, the runtime will load the program and execute the instruction. So this is pretty much the ExecuTorch workflow. And here is the example to run Llama 3.1 A billion on Android devices. And the QR code can be used to try it out. We also support multimodality. We support running Llama 1.57 billions on Android. For some reason, like it should be a GIF image, but it's not playing. But yeah, I think it's like in the QR code, we can see the same demo there. Why do we want to use ExecuTorch? PyTorch empowers AI researchers already nowadays, but the path to deploy the model on Edge is just really fragmented and complicated. We would like to support it in a principled way. For example, we want to leverage hardware accelerators for optimum performance, and user can easily follow the similar workflow to target the different devices. Our runtime can also runtime can target most devices, and we don't need conversion anymore. So here is the ExecuTorch timeline. We went through preview on October 2023, and we announced alpha on April this year, and we have our beta released last month on PyTorch conference. The official release for beta is this week, so it will include the performance Llama examples, and in the 2025 we will add more richer ecosystem integration and robustness. For beta, what is new? We aim to target stability, performance, and coverage, especially on stability. We target on API stability and also backward forward compatibility. On performance side, we focus on optimum performance on GenAI. For example, LLAMA 3AB and then Lava 1.57 billion. Of course, we also support the latest LLAMA 3.2, 1 billion and 3 billion models. And on the coverage side, we enable more kernels, and we focus on set up the benchmark infra and also the on-device debugging and profiling infra. Here, for the stable APIs, we set up the lifecycle from experimental to deprecation, such that like when user integrate to the latest code, it won't break their existing integration code. That's what one of the most important parts for our beta release. Here, I'm going to walk through the GenAI, the on-device GenAI use cases. CPU is a crucial role especially when we want to enable a wide variety of PyTorch models on ExecuTorch and experimenting novel research ideas like LLAMA quantization or LLM quantization. Right now, we can run family of LLM models and a wide range of other LLMs out of box for GenAI use cases. Our primary focus for our CPU performance optimization has been the ARM CPUs. We developed Gen kernels for Omnion to achieve peak CPU tokens per second on a variety of edge devices like Android and iOS phones, and also Raspberry Pi 5. Collaborating with Google, the new 4-bit Gen kernels are upstream to XMPAC, and working together with ARM, we also feature faster CPU prefill performance through Kaleido, which now has similar 4-bit Gen kernels. CPU is our baseline. In addition to CPU, a critical puzzle piece of on-device AI is the neural processing units, as known as NPU. It has more TOPS, which means faster prefill, and it is also more power efficient, which is crucial for battery life. Most software frameworks may not have the capability to efficiently enable NPUs, or the stack can be kind of fragmented. So we create a delegate API in ExecuTorch. NPU can be accessed by delegating part or the full PyTorch program to the corresponding backend. So we collaborated with Apple, MediaTek, Qualcomm, etc., to integrate ExecuTorch into their development flows. Note that although NPU power is leveraged, we don't move away from PyTorch and ExecuTorch ecosystem. It keeps consistency when compiling the PyTorch program from server to device and help users to profile and debug on device. Now, as I mentioned, LLAMA 2, 3, and 3.1 and other LLMs can run on phones through these accelerators. We also support multimodals. Here's the examples to run Lava models with both image and text inputs. The image encoder has 307 million parameters with 8-bit quantization. The text models has 7 billion parameters with 4-bit quantization. We provide AOT and runner components with CPU optimization, and the QR code is the instruction to try it out. We are also going to support other modality like audio, video, and yeah. So to support GenAI use cases, above a number of techniques are used. So we list some of them, like 4-bit, 8-bit for LLAMA models. And to further improve the post-training quantization accuracy, we also integrated the new spin quant technology. We are also actively working on the other new technology like long context length, lower bit quantization, and parallel decoding. So yeah, so here is like for the on-device, like it's a sort of a short summary for the on-device LLM status. So on CPU, we have the optimum kernels. On accelerators, we work with our partners to lower LLMs running on the backends, including Multimodal, Qualcomm, and MediaTek. So right now, they are all enabled, and then the LLMs can fully run on these accelerators. This is like taking a closer look at like what is needed, what is the fundamental features needed to enable LLMs on Edge. So quantization like LLM, large language model, meaning the weight is large. So the first optimization we always do is quantization to compress the model size. Secondly, we need to optimize the memory. The bandwidth among different memory regions are just really different, and we need to plan them carefully, especially when we are memory bound. Decoding acceleration. So users just want to get the result right away when they type the prompt. Fine-tuning, we would like to fine-tune different LoRa adapters for different tasks, like summarization and writing emails. DevTools, it's a pain to debug accuracy and profile. And that's ExecuTorch advantage. We provide native tools, and like here's the example. Like say for example, when there's a prompt saying like how is the weather, and then if the LM start hallucinating, then it's really hard to debug, especially it's on device. So with our partners, we can help you to debug, even if it's inside of the black box accelerators. So here is like more concretely, like what is the exact techniques here. For quantization, there's like 4-bit linear kernel, KV cache quantization. For memory, like one example is like have KV cache state. And then we can also do cache application. For decoding acceleration, we can do batch refill, and we can also do speculative decoding. Fine-tuning, as I said, like LoRa is quite common. And dev tools that usually comes with profiler and also accuracy analysis. There are 2 more updates. In addition to GenAI support, we also enable OSS reproducible performance benchmarking infra, either like on-demand benchmark request, or we can also schedule benchmarking to monitor the performance trends. They will go through the GitHub actions, and then the benchmark will run on AWS device farm to generate the performance matrix. We are also working on these experimental features on device training and fine-tuning. By design, it's composable with the existing ExecuTorch flows and backends. On the right-hand side, we show a convergence of loss when fine-tuning LoRa 5.3 models. Since it's a proof of concept, there's still lots of ongoing work and feature planned. Yeah, check out our repo. Ecosystem and community adoptions. So ExecuTorch does not work alone. It starts from torch.export, where the compute graph is captured with dynamism. Quantization is supported by Torch.io, where the lower bits quantization kernels quantization API will be hosted. We built this LLM vertical stack with Torch Chat to showcase LLM inference on mobile devices. Torch Chat is a PyTorch library showcase how to run LLMs across laptop, desktop, and mobile. For model sources, the model can be fine-tuned models from Torch team with PyTorch native support. We also partner with Hugging Face as well to make the models ExecuTorch compatible, like Gemma 2B and 5 Mini. ExecuTorch ecosystem is built with all the parts working together. Even though ExecuTorch just come to beta, we have seen active adoptions. It has been adopted by Meta products. So ExecuTorch support Ray-Ban Meta smart glasses, Oculus Quest 3, and Meta apps like Instagram and WhatsApp. it has been used by developers in the community. So example including like in painting mobile apps from Software Mansion. It's based on efficient SAM and swing transformer and use core ML delegate for acceleration. ExecuTorch is used in the inventory mobile apps like Diksha, running CV and OCR models for medical devices. We see researchers are adopting ExecuTorch as well, example including mobile LLM, AQLM enablement, Windows enablement, etc. So coming back to the first slide, we provide ExecuTorch as a PyTorch platform to help deploy LLMs and many others to edge devices. It will be like this week. It will be the formal beta status. Yeah, you're welcome to visit our GitHub repo and try it out. Yeah, so that is pretty much my talk, and I'm happy to take questions if there's any.
Thanks a lot, Chen. It was really a great talk and rich of many information. There are questions from the community. Let me go through some of them. Chan Seok is asking, for example, if there are hardware dependencies for the ExecuTorch model inference.
So it depends. Well, I think ExecuTorch itself is targeting on like portability, meaning like the ExecuTorch runtime, it can run like on pretty much everywhere. And now when we talk about like running ExecuTorch model for inference, say for example, then like usually user will have some hardware on top of their mind. Like if user want to target iOS, that's totally works. And if user want to target Android, that will works. And if user want to target Raspberry Pi, then that will all works as well. But for the ExecuTorch runtime, it doesn't really have it's designed to be portable. Like it's supposed to run anywhere.
Okay. And let me complement this question with maybe a comment. How would you consider easy or hard the interface of ExecuTorch to custom-made NPUs? You know, is there a fair amount of work to be done? Maybe some of these NPU, sorry to interrupt you. Maybe some of these NPU in the future will feature also ad hoc accelerators, optimized memories, maybe in-memory computing, you know. Any comment in this direction?
Oh, that is a very good question, and it also like part of the topic here. So the goal for ExecuTorch is make it easy to use for users, and it's aimed to like both unified and also aim to fast. I agree that like say for example the NPU can have like a dedicated path to like further like to make it really specialized and then performant. However, like for example, if I'm just a ML researcher and I may not know that much about this specific NPU, and I need lots of background knowledge such that I can deploy my models on the NPU, and I may need to follow a different instruction. Like, yeah, so there's like lots of burden there, and the path can be really fragmented. So for ExecuTorch, our goal is like it's a unified way. So if I'm researchers and the line of code to target, say, Apple's NPU or versus like Qualcomm's NPU or like MediaTek's NPU, the flow is pretty much the same. So user doesn't need to like really look into like how this specific NPU can work. Yeah, that's like I think the advantage of ExecuTorch. So we hope like it's pretty much like user doesn't really need to like know all the details for this NPU, but they can just run it and then it will just work.
So it means, thanks, Chen. It means that it's abstracted enough such that I don't need to be a super expert of the hardware underlying, because it would require much investment in knowledge. Right?
Yeah, that's expectation.
That's
And with the default path, we also aim to like have the best performance as well. So yeah, as I said, like we wanted to like provide users a unified way. Like essentially the flow is unified, but it's also like performant.
Thanks a lot. Let me go through some other questions. For example, from Davis, you spoke about 4 bits, but Davis is asking if there is or will be support for FP16 or other formats, mixed precision. Mixed precision can be a great configuration for generative models at the edge.
That is an excellent question. So yes, ExecuTorch supports FP16, and for the hardwares for the NPU, as long as they support FP16, then it will just work. Say for example, if once NPU they support FP16, it will just work out of box. Regarding the other lower bits or mixed precision, yes, they are supported as well. We are bringing up a list of lower bits kernels, like including 2-bit, 3 bits, all the way to 6-bit or 7. I think it's up to 6-bit. I'm not sure about 7-bit, but we support a list of lower bit kernels, and then it's up. It's like it can be used. And then like for the mixed precision, yeah, so I think that's part of like our quantization framework. We support custom annotation, and then essentially like user can decide like how I would like to quantize my input, activation, and weight, etc. I understand like mixed precision is actually very important, especially for LLMs. Well, I guess maybe it's important for other models as well, but like for mixed precision, yeah, in short, it's supported.
Thank you. And staying a bit on the quantization topic, there is a question from Chan Seok about QAT, quantization aware training. What's the kind of support you have?
Yeah, it's supported. So yeah, for the our default backend is the CPU backend, and it supports QAT. And pretty much every backend has their own quantizer. And yeah, so I think quite amount. I think currently the CPU support ExecuTorch itself support QAT, and then whether or not this backend can support build QAT is based on the backend's implementation. I think currently Qualcomm is also investigating QAT as well. Like I think it will be up very shortly.
Thank you. Thank you so much. There are also other execution models out of there. For example, Javen is asking about TVM. Any comparison? I would generalize also to, I don't know, any other interpreter that you may have already considered.
I see. Yeah, that's also good questions. I think TVM is probably like like a different ways. I think ExecuTorch. I guess like I'm not quite sure the latest status for the TVM. So, but I can tell like one advantage from ExecuTorch compared to other framework is that it's leveraging the latest torch.door export, and then the benefits of like I think there are mostly 2 benefits. One benefit's like it carries over like all the information from the PyTorch source code all the way to the on-device runtime. Like meaning like say for example, if I have a PyTorch model and I author it on server, and then like somehow like it's just error out inside a NPU. And via other framework, it could be kind of tricky to figure out how to find out where it goes wrong. But like via ExecuTorch, we have the native support, and we can help you to find out like where, like say for example, why it's slow, and then also like which line might be wrong. We can help you to find out the exact PyTorch line of code in the source code. Yeah, essentially like easy to use as probably like one of the thing out of my mind. But I guess like they both have their own, but they like TVM might have their own advantage. I probably don't have enough knowledge for like for this comparison here.
That's fine. And another question maybe is obvious for you. Anis is asking if Llama, the Meta Llama, has ExecuTorch support now.
Yeah. So like all the, well, I guess like for the smaller version, like Llama, for the ExecuTorch, we support Llama 2.7b, we support Llama 3ab, 3.1ab, 3.2, 1b, and 3b models. So yeah, pretty much like all the models that can fit to the to the RAM, then we can run it.
And another question from Nick: what are the memory footprint requirements from Llama 3 8-bit? Let me also add, in general, any comment you may share about the capabilities of ExecuTorch to deal with the memory system of the target in order to optimize its usage.
Wait, so I guess like the question asked here is the memory footprint requirements for the Llama 3AB, and what is your part again?
And if you, after you answer this question, maybe if you can comment about the capability of optimize the memory usage of the target from ExecuTorch point of view. You know, embedded system has a lot of constraints in terms of hardware, in terms of embedded memory.
I see. Yeah, that's actually a very good question. I think for the footprint, I think in the GIF we actually have it. I don't have the exact number, but what I can say is like the memory weight, the model size in total is around is less than 4 gigabytes, and because like we can run it on iOS, and for the iOS, the app will be killed if it's over 6 gigabytes. So I believe it's less than 6 gigabytes. We did some profiling before for the memory footprint. I just don't quite remember the exact numbers. Here's I can also like briefly mention like essentially like how the memory planning works here. So for the memory footprint, we actually have the toolings to figure out like how much memory is needed when we just export a model, because like it's pretty much like it will be just have the model weights that is like constant memory, and that's like less than 4 gigabytes, and then we have the and then also for regarding how memory works in ExecuTorch, the way it works is like we pre-allocate a chunk of memories, and then we will plan them carefully such that we can reuse some memories like when this tensor is no longer needed. So we actually have the tools to find out like how much memory is needed there. Yeah, I hope. And then like based on the tooling, we can figure out like we can continue optimizing it.
Thank you so much, Chen. I encourage you to share more numbers later on if you have time on the comment sessions because people are really interested. And I think I can also say the ExecuTorch investments and the impact on the community is really interesting. It's incredible how Meta is investing on the edge. That's fantastic. And thanks a lot for your time, Chen, and to have accepted to stay with us and to present ExecuTorch, and for the passion to reply to many comments, and there would be many other in the future, I'm sure. So thanks a lot for your time and a great talk.
Yeah, I will leave the answer, like I will continue answer the question when I go there. Thank you.
Sure. Thank you, Chen.